Okay, today I want to talk about phase diagrams. Phase diagrams are kind of a cool way to graphically represent the different phases of matter for a particular chemical compound given specific conditions. So this is the one for water, and I want to just kind of draw your attention to a couple things. First of all, the x-axis here is temperature, and the units here, so this is temp, the units here can be either Celsius or Kelvin, it kind of just depends. And then the y-axis, so kind of going up and down here, is pressure. And again, the units on that are going to be different depending on the different pressure units that we're looking at. So if we look at this one, we're in atmospheres, and we have temperature in Celsius. Now, a couple things to be aware of. When we're looking at this, we usually are given the 3 different regions. So if I have really low temperature and high pressures, like we do here, then we have a solid. If we have kind of somewhere in the middle, as we increase the temperature here, then we have a liquid. And as again, we increase the temperature here, then we end up in the gas phase. So this is always going to be the case for our various phase diagrams. If you look at this labeled point here, this is called the triple point. The triple point is this point right here that's at equilibrium for all 3 phases. So at this temperature and pressure, I have ice, water, and water vapor all at the same time, all in dynamic equilibrium, meaning that the rates of creating all of those and forming all of those are equal. And so that's our triple point. The other important point is our critical point up here. The critical point is kind of the point past which no return. And it's really, once we go too high of temperatures, too high of pressures, then we aren't ever going to have anything but a gas. And this kind of gas-liquid hybrid phase is called a supercritical fluid. And so we can see that in this particular case, it sits at about 374 Celsius and 218 atmospheres of pressure, which is a lot of pressure. And so that's kind of the point that we don't have anything but this kind of weird gaseous phase. So these lines then represent the equilibrium between the different phases. So this line right here is the equilibrium between the solid and the liquid phase. So we would call this the melting point curve. So if we're thinking about equilibrium, the solid is in equilibrium, which I'm going to show with arrows kind of going both ways, meaning that the solid is forming the liquid is forming the solid at the same rate. And this curve here is my vapor pressure curve. Vapor pressure curve. And that indicates that the liquid and the gas phases are in equilibrium with each other. Okay, so the rate that the liquid is forming the gas is equal to the rate that the gas is forming a liquid. So condensation, evaporation are happening at the same rates. And that's true across any point along this curve. And so any of these temperature pressure combinations will give you those equilibria. And then of course we have that here with this one too. This is the equilibrium between the solid and the gas. So this is kind of our sublimation, which we do see with water. You'll see sublimation that occurs sometimes in your freezers when your ice cubes get smaller over time. So it takes kind of cold pressures over a lot of time. Time isn't a factor on this particular graph. We're just looking at temperature pressure combinations. Okay, so if we're kind of flipping through then, and we're looking at some different phase diagrams, this is the phase diagram for carbon dioxide. So a couple things to kind of keep in mind. My D here is my triple point, so that's the point at which all 3 of the phases, solid, liquid, and gas, are in equilibrium with each other. And then E is my critical point, so there's that critical pressure, critical temperature, past which it can only exist as this supercritical fluid. So if I'm looking at this and I said, well, what phase is carbon dioxide at 1 atmosphere of pressure? And let's go 200 Kelvin. So what phase am I in? Well, if I'm looking at my axes, and this is another thing to keep in mind with these, the axes sometimes have this kind of weird spacing of things. So the scale on our axis is a little bit bizarre. So I'm going from 197.5 Kelvin to 216.6 Kelvin to 304.25 Kelvin. And here's 0 Kelvin, right? Here's absolute 0. And then our first data point is this, and then we don't have even spacing along the way. Same here with my pressure. I'm going from 1 to 5.2 to 73. So you can see that the scaling on this is exaggerated so that I can get all 3 phases in this phase diagram. So you have to keep in mind the units and the values on each side when you're taking this into account. Okay, so what phase am I at? At 1 atmosphere of pressure. So that's this one right here. So here's my 1 atmosphere of pressure, and 200 Kelvin would be kind of somewhere in between here. So if I'm 1 atmosphere of pressure, 200 Kelvin, that puts me about here, which means that I'm in the gas phase. Okay, which makes sense because 1 atmosphere of pressure is normal atmospheric pressure at sea level, and carbon dioxide is a gas under standard type conditions. 200 Kelvin is a little bit low, but it's still in the gas phase. The other thing that you can tell from this, which is kind of an interesting feature about carbon dioxide, if you look at this line, which is that kind of point where the solid and the gas are in equilibrium with each other, then we can see that there's a long stretch of this. There's a lot of values that I can go directly from the solid to the gas, and that there's only this really small region where this thing can actually be a liquid. And that kind of helps to explain why carbon dioxide sublimates. Because if I'm at atmospheric conditions and I increase my temperature, right, I'm just following along the x-axis here, then I'm just going to go directly from a solid to a gas. Or even at higher pressures, I increase my temperature, I go directly from a solid to a gas. If I get higher pressures still, so we're talking about like, underwater kind of things, then I could go to the solid to the liquid phase, liquid to the gas phase. So we can have liquid CO2, but we have to have the right combination of pressures and temperatures. So that's carbon dioxides. Let's look at carbon. So this is just elemental carbon. Carbon is interesting because it has 2 what are called allotropes, and that's what my meme here indicates. So allotropes, which means that we have 2 different solid phases of carbon. So 2 of the same phase, but 2 different types. There's 2 different types of carbon. I can have graphite or diamond carbon, that is solid carbon that exists in the universe under standard conditions as graphite. Again, if we think of standard conditions as kind of 1 atmosphere of pressure, which is here, 10 to the 0, of course, is 1 atmosphere of pressure. And temperatures that are reasonable. This actually has a reasonable scale here, 2,000, 4,000, 6,000. So if we're kind of down here, then this is where carbon is most of the time in the graphite kind of scale. So what do we think about the triple point? If we had to guesstimate the triple point for, let's say, the gas, the liquid, and the graphite phase, so gas, liquid, graphite phase, that would put my triple point here. Then if I had to guesstimate what that value is, then I'd say it's probably somewhere lower than 4,000 but greater than 3,000 if I'm kind of giving myself a center point there. And then in terms of pressure, probably a little bit under 10, right? So that's kind of guesstimating what I'd need to do. Now these conditions are important because if I can create these conditions in a lab, or if I can find these conditions that are naturally occurring, then I can create the phase of matter that I'm trying to get at. So that's kind of why, we always joke about putting charcoal under pressure and getting diamonds, right? So if I have a normal temperature, so let's just kind of put it at where our normal temperatures are. If I put graphite under enough pressure, so the graphite from your mechanical pencils under enough pressure at the same temperature, reasonable temperatures, then it will ultimately form a diamond. I mean, these pressures are crazy, but it will occur, and you can see why that happens then on these phase diagrams. Now let's go back to water. Now, we don't usually think of water, and I realize my scales are a little bit out of the frame here. This is still temperature. It's in Kelvin. and it actually has the Celsius scale here on the top. So this value is -40, -20, and 0 degrees Celsius. So sometimes you'll see phase diagrams like this with the temperature scales in kind of different ones, the corresponding ones at the right places. So my 0 degrees Celsius, of course, is down here at my magic number of 273.15, which we know is our conversion from Celsius to Kelvin. And then my pressure here is in megapascals. So mega as a prefix means 10 to the 6th of normal pascals. And Pascal, of course, is our SI unit for pressure. So my solids then here, just to give you an indication, 1 megapascal is equivalent to 9.869 atmospheres. So we're used to kind of thinking in atmospheres because atmospheric pressure is what's over us at any given time. And so we're talking about hundreds of these atmospheres. So we're talking about very high pressures. And you can see that I have different phases or different allotropes of solid water. There are actually 14 solids, which is kind of crazy, right? There's 14 different types of ice. This one has ice 1, 2, 3, and 5 in it, but these different ones have different structures to them. They have slightly different looks to them, and they exist under slightly different conditions. So if I had ice 1, let's say, and I want to make ice 3, so let's say I'm at 1 atmosphere of pressure, so I'm down here kind of low, and I'm at, let's go 250. So let's say that I'm right here. Then what would I have to do to get ice 1 to form ice 3? Well, if I'm at this particular temperature, I could get there straight. Not that that line is straight, but you know, use your imagination. By just increasing the pressure by quite a bit, right? So I'd have to add a great amount of pressure, and then that ice 1 would become ice 3. So that's kind of the way that we could use this. I want to get to ice 3. How would I do that given the conditions that I'm given? Now let's go back to waters, because not only is water fascinating because it has 14 different solid types at the time of making this video, and all of those 14 would still be in this solid region, but it also is interesting because of the slope of this line, the line that's between the solid and the liquid. So if we look at this here, and we're thinking about the slope of this, then as we are increasing our pressure here, so let's say that I'm here at 0, right? Here's 0 degrees Celsius, and I'm somewhere less than atmospheric pressure. If I increase the pressure, then I go from a solid to a liquid. Now that goes against everything that we've learned about solids. We always learn that solids are dense. We know that liquids are more fluid and can move around. There's more space between the particles. But water is weird because when you put pressure on it, the more dense form is the liquid form. So liquid water is more dense than solid water. And you guys already know this because solid water floats on top of liquid water, right? You put ice cubes in your glass, they don't sink to the bottom, they float to the top. That should blow your mind every single time you get that glass of ice water, right? It floats to the top. No other solids do that, or very few other solids will do that. Most of the solid forms are more dense. So the slope of this melting point curve being negative, right, kind of going in the opposite direction there, indicates that the liquid phase is more dense than the solid phase. Pretty wacky. And you actually already knew this too, because you learn early on that water expands when it freezes, right? Have you ever taken a water bottle and you fill it with water and then you throw it in the freezer because you want to chill it down, but then you forget it exists, and then the water bottle explodes, right? The cap comes off because your water expanded. If you have expansion of a solid, that means there's more space between the particles. That means that it is less dense than the liquid phase that you had put in there in the first place. So water is so incredibly cool, and the phase diagram just starts to get at why, one of the many reasons that water is so neat. All right, as always, if you have any questions, don't hesitate to reach out. Otherwise, I'll talk to you again soon.